My talk today is called Through the Ocean to the Mantle. And remember the picture of that layered Earth, the two, some approximation, the onion-like nature of the Earth that you saw as the picture here, that's the mantle, but I'll return to that. And this is work that is ongoing. In fact, last week I was in Japan with my student, a Portland native, Joel Simon, deploying one of these seismic robots that I'll show you now. And I'll tell you why we're doing it, and I'll tell you what we're doing with it. If there are any questions, please interrupt me. There's not enough people here to make that a hassle. Shout out if you want me to stop or clarify something. And I should also like to thank the organizations that brought me here, and that's the IRIS, the Incorporated Research Institutions for Seismology, which is a consortium of academic institutions that get together to do global seismology. And so this is all of us interested in earthquakes and plate tectonics and the deep earth that share all of our techniques and all of our data. If you go to their website, you're interested in a particular earthquake, you can get the data from all of the hundreds of seismometers that contribute their data to their data center, which is based in Seattle. And you can look often in real time what's going on. They have amazing visualizations, they have amazing teaching resources, and they have amazing outreach. But the backbone of it is all of us academics, primarily in the US, but also worldwide, that just agree to share freely the products of our science with each other and with the public. And then also with the Seismological Society of America, which, as the name implies, is the Society of Seismologists in America. Okay? And they are also including, of course, the exploration seismologists, the ones that explore for hydrocarbon resources, the engineering seismologists, the ones that try to keep ourselves safe by designing building codes and looking at the response of buildings to earth shaking, and then the academic seismologists who are pretty much interested in everything else, including the very, very deep earth where we have no reason to go. We will never go, but we are just literally curious about what makes it up on the inside of the earth. So I'll briefly introduce this large subject here by making a few points. And our Earth is, as you know, it's a collection of minerals. And there's some liquid and there's some ocean. And it's chemically differentiated. It's not everywhere the same. That which brought together our planet from the initial cloud of dust that it was in the process of planetary formation, it all sort of separated and segregated and sank to the bottom and became primarily layered through gravitational settling. And then through to plate tectonics, we're having the vast differences between oceans and continents and volcanoes and faults and so on. And if you want to just summarize what the main differentiators are, well, it's either what it's made of, the composition, or how hot it is, the temperature. So I'll be talking a lot about the compositional and thermal heterogeneities that make our Earth interesting to look at, and especially not to first order just that layered structure, that the various three-dimensional differences that make it a very, very interesting and dynamic body to look at. And the way that we're doing it is that, well, if the material changes, like from a liquid to a solid, or from a hot solid to another hot solid, or from one mineral type to another mineral type, it affects the speed with which seismic waves propagate. Seismic waves are those waves that are sent out, radiated by seismic sources like earthquakes, but also explosions and man-made events such as nuclear explosions, for instance. And they're called seismic, they're elastic waves, they're not acoustic, they're not like sound. They have multiple ways of moving through the solids as they do. And depending on the material that they travel to, their speeds are varying, and that is what we try to measure. But also, if you change the material in the Earth and you change the temperature and you change from the liquid to the solid state, you're going to feel that because the mass density will be different. And the mass density is measurable to great, great precision by a variety of tools. Handheld gravimeters, like you have in fact an accelerometer in your iPhone, to relative gravimeters, with which people found the oil reservoirs in this country over 100 years ago, through the very sensitive instruments that are flying on satellites that are measuring our gravitational field. I walked through the museum this afternoon. I saw a video of the GRACE satellite, which keeps measuring the time-dependent gravity of the Earth, and that is actually sensing the melting of polar ice caps, because as that ice melts, that mass is gone, and that satellite pair, which flies at 450 kilometers high, over 350 miles high, is sensing the difference due to that little bit of ice, the millimeters of ice that are shaved off ice sheets every year, which ultimately is billions of tons, but it's still amazing that that is so sensitive that through gravity we can find that from satellite height. And then finally, just looking at the Earth, just looking at the shape of the surface of the Earth has an enormous amount of information. And I'll be calling that the Earth's surface topography, which is the heights of the mountains and the depths of the valleys and the shape of all of these things, which ultimately reflects not only what happens at the surface with climate and rain and weather and erosion and the shaping through glaciers and rivers, but also what happens on the inside. Large currents in the Earth's mantle tend to bring things up and suck things down, and by looking at the overall shape of the Earth, we are trying and capable of inferring what's on the inside that is happening. So, to understand Earth, and this holds for other planets, you may all have heard of the booming interest in exoplanets these days. We're finding hundreds and thousands of planets in the solar system, and looked from a large distance, all we often only have is a size, in other words, a radius, a mass, a shape, if we are lucky, a gravity field, if we are lucky. In other words, these physical observables are what we use as geophysicists to study those planets that we are continuing to discover as we go along. So, elastic wave speed, remember that's the speed of seismic waves, and the mass density, that's what we can recover from gravity, and then the height of the mountains and the depth of the oceans and so on, that is that topography. Okay, so topography, let's take a look at a picture here. Topography is a model, okay? So if you're Googling Earth's topography, you'll find plenty of pictures, but you'll also find various scientists who make their models of topography. And this is not it's a subtle point perhaps, but it requires a measurement and it requires a reference, and this is one particular one. And all of you, of course, recognize the Earth, and you recognize the continents, and you recognize that the Himalayan plateau, for instance, is very, well, let's see, does that even work? I have to turn it on. Okay. So the Himalayas, the Tibetan plateau, here are some of these ridges in the ocean, the subduction zones that we're seeing here, the trenches, the deep trenches where the crust gets consumed by going down. And what you're looking at is plate tectonics from a distance. Here's a picture of the Earth's gravity field, and here, this is probably less familiar to most of you, the acceleration with which objects accelerate as they're released in free fall is not everywhere the same. Our planet has a complex shape, it's also rotating, it's flattened, and the three-dimensional structure, in other words, that material that makes up its inside, causes this gravity field to vary everywhere we go. The acceleration due to gravity is a different value everywhere you go. And here's a picture of what that looks like, and I've taken out much of the variations due to the Earth's shape and its rotation, and I'm only showing the very, very small differences of where, if it's a little more or a little less, we are seeing a little more gravitational acceleration or a little less. And so we're seeing essentially, again, the expression of plate tectonics, ocean trenches, ocean ridges, ocean islands, and so on. And all of those are reflective of all of the interior mass on the inside. Yes, please.
How much can it vary as the extremes?
So in this particular map, where we are taking out the effect of the Earth's rotation, which is massive, and the Earth's flattening, which is also massive, that's about a part in 300. What we're showing here is something that is 100 units of 10 to the negative 5 of gravity. So this is about a part, our sensitivity of our instrument is down to about a part in a million or 10 million of drop in an apple. That's how sensitive we know it. And several hundreds of these units are these variations. And so you can buy a handheld gravimeter. They are sensitive, they are expensive, and you can literally walk across the surface of the Earth, as people used to do, and you can pick up these tiny variations in units of 0.1, and then it goes up by about plus several hundred and negative several hundred. So it's a large dynamic range and very sensitive instrumentation, and we're seeing that all the way from satellite height down to handheld instrumentation. So then earthquakes, okay? Some points to make are that earthquakes are, of course, they're happening all the time. And this question of how large they can be and how small they can be, well, they span the entire range. You've heard of magnitude 9, that's obviously a very large earthquake, they're very rare. But 8, 7, 6, and so on, they're increasingly more common. And by the time you're in magnitude 4 or 3, they're happening essentially all the time. Here, I'm plotting the locations of the Earth's earthquakes in the last 30 years. And once again, they delineate the Earth's active zones of deformation. And so you think again of that plate tectonics, which is, it shows you where areas are of destruction, the subduction zones, and areas of crust creation, the mid-ocean ridges, and then the odd intracontinental earthquakes that are often causing the damage that we are trying to guard ourselves about. If you're thinking magnitudes 5 and 6 and 7 and 8 and 9, in this catalog, there's about 2 earthquakes a day. So as a practicing seismologist, when family and friends tell me, oh, there was an earthquake, are you excited? I'm like, no, there are very many earthquakes. Of course, the big ones, the shallow ones, and the ones that are happening near us, those are the ones that we are sadly excited about, which we definitely need to study because they lead to human suffering. But by the time you're in the deep Earth, in the distant Earth, those earthquakes are a dime a dozen. But every one of them is a source that sends out energy, that sends out seismic waves, and that is what we're trying to measure, to try to image the inside of the Earth and to see what literally it is made of. So chemistry is what atoms and molecules make up minerals, and chemicals have physical properties like temperature and mass density. How hot is it down there? What is it made of? And how much does it weigh per unit mass? So again, gravity and seismology give us the constituent sciences, the constituent elements of what goes on in the deep Earth. So I will give you an example of an earthquake here that happened offshore Oregon. And we now know, thanks to 100 years of study, so much about seismology that if we characterize the earthquake source, its location, its timing, and the type of mechanism, like if it was a thrust fault where one thing goes down, or a normal fault where one thing goes up, or the other way around, or a strike-slip fault where things slide past each other, then numerically we can calculate what the wave field is that is experienced by the Earth. And then we can compare that to our observations and refine our models. So for every reasonably large earthquake, Princeton University, through my colleague Ewan Trump, has a so-called shake movie. And you can plug in your coordinates and you can see, has there been an earthquake? And then you can see what the predictions are of the shaking everywhere due to that earthquake. And then through IRIS and the Seismological Society of America, you can get data that correspond to it. So here I picked out an earthquake that happened in January of this year, a magnitude 5.6. And just to get a bit of a global view of what's going on here, the second mark is right there. So there's stills from the movie. This is after 1, 2, 6 minutes, 8 minutes. So this is the shaking. The colors are up or down, and you see that radiation where that like ripples in a pond, but not quite like it, because there's diving waves, and then there's surface waves. There's those Rayleigh love waves, as they're called, on the surface, and then there's the various volumetric waves that are bouncing up and down inside the Earth. And these calculations here show what we can expect at literally every second after the earthquake. I'm downsampling it here just to show you the most salient features. So if you put a seismometer in Ottawa, then at this point in time, that's marked by that number there, you're going to see a certain shaking, you're going to see a certain seismogram, and you're going to be able to compare that with predictions from this earthquake. So collapsing down to offshore Oregon, this is a strike-slip fault. You see the radiation pattern. You see that it's sort of split into 4 quadrants here where up and down alternate. And it sends out waves, surface waves and body waves, and various other scattering waves and bouncy waves and reflected waves and transmitted waves. And that whole zoo of waves is all predicted by a numerical model that takes as input, where's the earthquake, what type of earthquake is it, when did it happen, and what sort of earth is transmitting that energy. Here's another look here just to introduce to you that, first of all, we measure the distance along the surface of the Earth in degrees along the surface of the Earth. So for an Alaskan earthquake that happened right here, this is going to be 20 degrees, 40 degrees, 60 degrees, 80 degrees, 100, 120, 140, 160, and by 180 you're at the antipode of the earthquake. So that's why we talk about degrees along the surface between 0 and 180. And the red triangles here are the hundreds of stations that IRIS here collects data from. So if there's an earthquake tomorrow, then you can probably get all of the records for all of those stations online in almost real time through IRIS. And so that is the mature stage that we have gotten global seismology into, where for every earthquake, those sorts of plots are automatically generated, those data are automatically posted, and the global community can use those data and then study either the earthquake or the structure of the Earth through which their energy propagates. If you have been waiting for a seismogram as a wiggle on a screen, well, here is a collection of them. In terms of these degrees, the distance across the surface of the Earth between 0 and 180, and then in time, in minutes since the earthquake, here you see the arrival time of the various phases. And so I mentioned the body waves that are going through the Earth, the surface waves that are propagating slower along across the surface of the Earth, the bouncy waves that go down to the core and bounce back up, the transmitted waves that go through the core and come out all the way on the other end. All of these phases are apparent from this almost raw data plot here. And so we are looking in very, very much detail at literally every wiggle of every seismogram that we can get our hands on, thanks to all of this data exchange that an organization like IRIS makes. So that's our primary data: earthquakes and seismometers, okay? And so I'm going back to the cartoon version here. We have earthquakes all around, handfuls a day, and we have a lot of seismometers on land. And I'm just showing you some direct array paths between an earthquake and a station, one type of wave, in other words, to tell you that these mechanical disturbances that are seismic waves quite literally go through the actual Earth. And key observations that we can make, well, the very fact that rays go down and the energy comes back up, that tells us, like refraction in a pond or in a fish tank, that the wave speed must generally increase with depth, which is consistent with the fact that the Earth gets under higher and higher pressure as you go deeper in Earth. But then remember again that the fluid outer core here is a particular type of medium, because it then, well, first of all, it's fluid, and it's a liquid, and then it goes back to the solid state here in the inner core because the pressure wins over the temperature. It's very hot in this iron core, but it's not quite pressurized enough to be not liquid, and so this light gray is liquid, and this darker gray is solid again. It's, of course, in that outer core, this liquid outer core, if you're interested. That is, because it's liquid, it's also moving very fast, and that is the source of our Earth's magnetic field. That's the source of the geodynamo that makes our magnetic field. Then we also notice as a first order observation that if certain waves, certain rays go down into the Earth, and sometimes they reflect quite sharply, and so that tells us that there must be sharp interfaces in the Earth. A couple of examples are, of course, the outer core and the inner core boundary, but also here another major boundary here that reflects the change of certain minerals into, they transform into a different state, and that state changes their density, that changes their elastic parameters, that changes their seismic velocity, and so if a seismic wave comes down to it, much of it gets reflected, and we see that right away by almost simply plotting the earthquake seismograms here. Now, and then the fluidity of the core is because a certain type of wave completely vanishes. You cannot sustain any shear wave in a fluid, and because that is so directly apparent from looking at the record, that's the prime evidence for the liquidity of the outer core. So that's general observations from seismograms. Now let me just divide earthquakes between the ones that are local, where, okay, an earthquake gets recorded close by. Something that we call teleseismic, like a television, which is a distant vision. This is a distant seismic, where in order to connect the source to the receiver, it must go down deep. And so this is, because it's distant, we infer that it has gone through deep material. And then, of course, things like core phases, which go all the way down to the core. So these are just three examples of body waves that are going through the Earth. And if you can connect an earthquake to a source, you can also connect it in a bouncy way, in a multiple bouncy way, and over the surface. And so there's a large variety of waves, but these are just a few examples here. And the teleseismic waves give us information about the mantle, because after all, as I'm saying to you, they go through it, so they carry information about the medium through which they travel. Okay, so this is the worst figure of the talk. I couldn't get this to be better, but so it's a random seismogram from a random earthquake. And what you're seeing is the arrival of energy in time. A blip, not much, another blip, a large blip. These are the body waves, okay? So they are small in amplitude, but they go fast. And by the time you're at the surface wave, that's what does the damage. That's what shakes your buildings, because they're large in amplitude, but they take more time. So if you're interested in early warning of earthquake, as I know the state here is, then it's about trying to detect the early arriving little bits of energy that foretell the later, soon-to-be arriving large amounts of energy. And this distance in time here, the seconds to minutes that you may have, depending on where and what kind of earthquake it is, in principle gives you the early warning with which you can do things to protect yourselves from the effects of it. But for us here to figure out what the inside of the Earth is like, we're going to compare the data in black from the model, like I showed you in that animation, the numerical simulation. And because we don't have the Earth quite completely figured out yet, there will be differences. And so we're going to, in general, start looking for where our model doesn't quite match the data, where it's a little large, or a little small, or a little early, or a little slow, or a little wide and a little small. And we're going to try and adjust our Earth model such that we are arriving at a complete match between the data and the model, which is basically all that science does. Make a model, make a prediction, compare it to data, see how bad it is, and then go again and try to make it better. There was a question up there.
John, generally, how far is the distance between the first waves and the big wave?
It depends on distance, because the speed with which these waves differ. If they have to travel a larger overall distance, their separation will increase. So that is a key element in certain early warning systems. If you're right on top of your earthquake, you're never going to get an early warning. They'll all be there at the same time. But if you're hundreds or thousands of kilometers apart, you will see those body waves come in, and then you have time to make a decision, because those surface waves traveling slower over a longer distance will give you more time. So it is a critical trade-off between the speed differences, which is pretty well known, and then actually where you are with respect to the active earthquake zones. So this earthquake offshore Oregon is several hundred miles off the coast, and you're going to get something like, I don't know exactly now, but you might have tens of seconds to prepare. Which is enough. It's enough for automated systems to detect the presence of the earthquake, to rapidly estimate the magnitude, and to maybe do a slightly better job, and then to send automated alerts, shut down power plants, stop elevators, send warnings. So California early warning, Pacific Northwest Seismic Center early warning. If you have 60 seconds, you can do a lot of warning, especially because the information that you send out travels at the speed of light over the internet with microsecond delays. Yeah.
As the waves propagate through the core, do they have a refraction angle?
Yes. Yep. So all propagation, every little bend is either smoothly or sharply refracted and reflected, and so yes, definitely. So the rays that I'm drawing are exactly like optical rays here. Now, in practice, there's more going on than that, but if you want to keep track of where the energy goes, it's just like optics. Okay, so, and just like optics, we're also going to try and image the inside of the Earth just like a medical tomography experiment would do. So, in the 70s, engineers and doctors figured out that by shooting X-rays at people and recording them at various source to receiver angles here and then rotating them around, that you could reconstruct the properties of the inside of your body. At around the same time, seismologists were starting to do the very same thing, using the earthquake sources recorded at various earthquake stations to figure out the properties of the inside of the Earth, beyond that one-dimensional layering structure that we already know about. And let me just give the example of a simple way of doing this, where let's say you have one earthquake and one station, and we know the average Earth well enough to figure out what sort of path it might take. And we compare the time that particular wave that we're measuring that we predict to the actual time that it arrives. And so if our Earth model and our calculation says it should come at 17 minutes and 32 seconds, and we look at the data and it says it came at 18 minutes 01 second, then we have a delay to explain, which means the Earth propagated that sort of energy slower than our Earth model. Now, knowing that it's been slow doesn't tell us where exactly it was delayed, because in principle, of course, this delay could have accumulated everywhere. Just like if you're traveling between Boston and LA, and you get there an hour late after a week, you don't know exactly where the holdup was. But like the medical tomography, if you have many, many crossing paths, many stations, many events, many ways of connecting that energy, and many ways of accumulating delays, and many ways of accumulating speedups, then you can figure out computationally where the Earth retarded the energy and where it sped it up. And then remember that we are doing this because we're trying to connect the slowdown and speed up of seismic waves to what happens, what the physical properties are of the materials on the inside, whether they're hotter or colder, made of this or that mineral in this or that particular state. Just like in the medical tomography, where from all of these measurements you're trying to figure out where's your heart and what sort of structure is it, And are there tumors or organs or things that aren't the way they should be? So this type of science has been done for about 30 years, and so we've accumulated quite a bit of evidence for what the Earth looks like. And I'll just give you 3 examples here that you might even have heard of. The lithosphere is the rigid outer part of the Earth. And so let me show you a cross-section through Australia from west to east. And as a function of depth here, 15 kilometers to 400 kilometers. Blue is where a particular type of seismic wave is propagating faster than the average over this picture. And red is where that particular seismic wave travels slower than the average over this picture. And we color them red because hot material, temperature anomalies, are often responsible for slowing down the waves. And cold material, blue, is often responsible for speeding up these seismic waves. And so I like to look at this picture and see the structure of the Australian continent as the sort of boundary between the blue and the red, where the continent goes down to a depth of about 200-300 kilometers. But if you're looking about 400 kilometers down into the Earth mantle here, you're back in sort of hotter than average material, and you have essentially lost all the knowledge of there being a continent on top of you. So, is Australia an island or a continent? Well, it's a continent because it's made of continental crust. But how deep does that continental crust go? It certainly doesn't go down all the way to the core, because in the core is the core, and that's all iron. That's no longer silicate. That's no longer minerals like bridgemanite. So this is the sort of picture that helps us figure out that answer, where we can also say, well, in the middle of the Australian continent, it looks like there's a deeper continental route, whereas in the east of the continent, because this material is actually younger, it seems to be underlain by hotter than average material, and indeed this is also a source, a fertile source for certain volcanoes that were active to a few thousand years ago. And so this is a picture of the upper 400 kilometers of one of these continents. Here's another picture of another main feature of plate tectonics is subduction zones. There, where the Earth's plates dive beneath one another. Here's now, again, the blue color scale. Blue means faster than average propagation, and keep thinking of that is a more dense, more rigid, more cold material that, because it's then also heavier, is going to sink down. And so everywhere where we see blue, we think of things that are dynamically sucked down by their extra weight and draw down and in other words, get consumed. And so here through this Indonesian arc here, you're seeing all these various ways in which that crust seems to be a slab of material that is drawn down into the mantle. Needless to say that all of these areas here are also active sources of earthquakes, because wherever there is these large pressures and that material being shoved down into the Earth's mantle, there's a lot of friction that generates the deep, large earthquakes that we have in this particular area. Finally, what comes down must go up, and so for every lot of material, there must be an equivalent amount of material that goes up for every downgoing material. In the upwelling regions of the Earth, we are giving the name of thermal plumes. And so, if you're with the color scale again, the plumes are going to be hotter than average, they're going to be less dense than the average, you're going to want to rise up in the mantle as large blobs or conduits of material. And here at one particular depth, I'm showing you a model of the areas in the deep Earth at also 400 kilometers that appear to be hotter than average, want to come up, and we think that those are the source of the large conduits of upwelling material. And if you want to think of volcanoes, that's fine, because ultimately that material, which isn't liquid, again, it's just plastically deforming, but by the time it's at the surface, it's going to be under, the pressure will vanish suddenly at the surface, and there that extra thermal energy is going to actually liquefy it and make it into magma, and thus volcanoes. So if you want to think of a mantle plume as something that could be Iceland or Hawaii or any of the large oceanic volcanoes or volcanic regions that you might be familiar with, the Galapagos and so on, then you'd be making the right inference, although this continues to be an active source of study. We do not know the Earth well enough to really know for every one of those volcanoes precisely by which type of structure it is underlying. But lithosphere, the rigid lid of the continents and the oceans, the subduction zones is wherever the material goes down because of its cold and dense and old. And then the mantle plumes are generally the regions of upwelling material that altogether define the large convective cell of the Earth, which is all fitting within that framework of plate tectonics. As you know, they then carry that lithosphere up and down the surface of the Earth, and plates are broken and plates are generated, and all of that, of course, generates earthquakes. So now I'm going to come to the problem at this thing. It seems like we know how to do a lot of these things, but of course there are residual problems. And the main problem that we address here is that we do not have earthquakes everywhere we want. Unlike in medical studies where you can position your X-rays and your detectors pretty much wherever you like on the outside of the human body, we need to take the sources of energy, which are earthquakes, as they come. And you've seen enough here to know that they happen primarily in plate boundaries, and we don't control them, really. So this is an example of a few days in 2003, plotted as a function of magnitude here, whichever earthquake were present during that handful of days. And you see it's not uniformly distributed. Here's another view of them in terms of distance from La Jolla, California, which is about here. And so these are close by, again, in degrees here, like in the first few plots. And then the distance gets to be darker and darker because it gets to be farther and farther away from that point near San Diego. Again, that's just a random couple of days in 2003. Now, if you looked at where the seismic stations are, I showed you the station map of the red triangles. There are definitely hundreds of stations everywhere, but you've also noticed they're mostly on dry land. That's because that's where we can walk. So if you plot a little circle of influence around most of the stations, then you're going to see that the coverage or the illumination by detectors is, of course, well done in the northern hemisphere continents, less so in the southern hemisphere continents, and then here and there on ocean islands we have put stations, but large areas, in other words, the oceans of the Earth's surface are completely not covered by any instrumentation. Now, people do go down to the ocean bottom to put seismic station, but it's always an expensive, a risky, and a temporary solution. And this is the problem that we have been trying to address with our research, is to actually go out in the dark areas of the map here and try to get more data, such that we can improve our knowledge of what earthquakes are there, nearby, what sort of earthquakes are recorded that come from afar, and what sort of gains we can make in terms of imaging the inside of the Earth's interior by collecting many, many more paths between earthquakes at various places and new stations that have never, that are in areas that have never had a station before. So about 10, 15 years ago, we looked at the oceanographic community, which has been and continues to do, deploying thousands of drifting detectors into the ocean. Everything now that we know about the top 1 or 2 kilometers of the ocean, its temperature, its ocean current, its salinity, and so on, is ultimately derived from these robotic floats that are very simple devices, very complicated in another sense, but they go down on a schedule They measure the temperature, the density, the salinity of the seawater, and as they do that on a schedule, their position gives you the ocean currents at these various depths also. I took a snapshot here on 6 December 2007 when there were 3,000. It's gone up to 4,500. It's back down to 4,200. This is a continuously replenished source of ongoing observation in the oceanographic community. So we, the seismologists, looked at the oceanographic community and figured, well, if they can get 3,000 these types of devices, maybe we can get a few hundred similar devices if we can turn them into seismometers that can record Earth's motion from seismic waves. This is another snapshot. This is from a couple of months ago. They were down, well, they were up from 3,000, but they were down from 4,000 and so on. So that was our question then. Can we actually, as the seismologists, knowing that we are this well-organized and relatively large community in the world, can we build something like the Oceanographic ARGO program? And at this point we said, yeah, we're going to try, and we invented an acronym. This is due to Chris Nolet, who was my postdoctoral supervisor. Mobile Earthquake Recording in Marine Areas by Independent Divers, and that of course spells MERMAID. Okay? So whenever I say MERMAID from now, it's a little concept of an instrument that is capable of recording ground motion due to earthquakes in some sense from within the ocean, like a little drifter. So at this point, I should also mention that this is not like all good ideas. It's not a new idea, because people have looked at the ocean forever and figured, what can we do to open this up to human inquiry? And I'll just give you a few examples from the 70s and 80s. They weren't called MERMAID, I'll call them proto-mermaids, just to give a tribute to the people who were very clever and tried a variety of instruments as early as 1970. 1970 here, this is Bradner, who threw a sphere, an aluminum shell, into the ocean with a 3-component seismometer that was keeping track of the motion of this device. And it was essentially set free in the ocean, and it had an antenna by which it could be recovered. And so this is the first floating seismometer, if you will, that was tried. Another type is a sonobuoy. This is a device that actually currently is still in use by the Navy when they're trying to detect submarines from their sound. It's a similar design by throwing out something that's freely floating and that records the pressure of the water. Here, 1973, it's a very grainy picture. This is all analog at that point, and so here you see a little P wave and a little S wave. Those are the compressional and shear waves that we've already encountered, and then you see another type of wave, that's a tertiary wave, which propagates in the sound fixing and ranging channel. That was part of one of the trivia questions. And so you see this sort of worked in the 70s, but it wasn't very good. It was all pretty noisy. The swallow float is the third type. I won't belabor the point here that people have been trying this for a number of decades. Now, all of you, I think, I'd like you to think about what we didn't have in the 70s and 80s and 90s that we now all have. Remember, detecting ground motion is one thing, or detecting acoustic pressure in the ocean due to ground motion of the ocean floor is another thing. But measuring this reliably in the 70s and 80s and 90s, what major technological invention have we had that you now all have in your pockets that didn't exist then? It was GPS, right? And GPS gives you exact time, because a GPS satellite is essentially a flying clock. And because it gives you exact time, you can figure out your position. And those are the two things that we need in seismology. We need to time the arrival of certain waves and do that to very high precision. And we need to also know where we are. And back in the 70s and 80s, they recorded earthquake and they had their time, but the clocks weren't very good and the locations were not very good, and so they really couldn't proceed. So, but by the year 2003, when we first put this instrument together, of course, we did have access to GPS, so we had excellent timing and we had excellent position. So we got one of those oceanographic floats, one of those ARGO floats, one of those things called SOLO, And we retrofitted it with a hydrophone, which measures the acoustic pressure in the ocean. And this is one of those devices that you can throw out overboard a ship, and then it will go down to a pre-programmed depth, and then it will sit there and float with the oceans and record everything that's going on. And when there's an earthquake, its brains, which we designed, recognize it as such, and then it triggers the signal that the instrument should go up and report data, so that we have a data point, which is a little seismogram in an area where nobody's ever been. Here's the inside of that instrument, if you're interested. It's essentially a pump that is able to adjust the buoyancy of the instrument such that it can descend into the ocean and then also come back up. We've also put a little flag on it so we can actually recover it at some point. So here is our very, very first MERMAID prototype of the year 2003 and 2004. So this whole mission design, and at this point I really like to use the word mission because it's like designing a space mission, except it's harder because the ocean is so much heavier, okay? If you're designing a satellite, it's of course massively expensive to get it into orbit, but once you're out there, and you're shielded from the sun, so fly at night, you're in no atmosphere, and it's an okay environment. But as soon as you're a couple of 100 meters down into the ocean, the pressures are really crushing you. So keeping track and not losing and properly designing these instruments is an ongoing battle that we are fighting. But so here's a mission design here. Throw a MERMAID out, it goes down to a depth, it floats passively with the ocean currents, and then it always listens, and when it has recorded an earthquake that our intelligence that we endow the instrument with decides is useful for our science, it'll come up and send the data to a satellite, and then it goes back down again. So now this is the business of doing science. You have one prototype, and you're scraping by on little funding, and you have a couple of days of an experiment, and then you finally record one earthquake. And then you are happy because you have a proof of concept. So this is the one earthquake that was large enough and distant enough to show to the community that it was doable. And that's why I'm showing it to you. This is from 2003 or 4 now, published in 2006. And so this was a magnitude about 6 at 46 degrees. Again, that's about 5,000 kilometers across the surface of the Earth. So that's in principle energy that came from a large distance, dove deep into the Earth, carries information about the Earth's mantle that we want to know, and was recorded by this autonomous device that was out there. And then we started comparing that sort of record with all sorts of other things that happen in the ocean. Because you now have to answer the question, or ask the question, well, it certainly is noisy in the ocean, right? There are animals living there, there are people there, there are ships there, there's all sorts of things going on. So after that one earthquake, let me just show you a couple of examples of what a noisy environment the ocean is. And I'm going to show you a couple of panels here. Here in the black, it's always going to be this pressure record. So it's the acoustic pressure inside of water, and it's, as a function of time, it's a little more, a little less, and so that's our seismogram, if you will. Not that there are any earthquakes. In the middle, it's a breakdown of what sort of energies there are, what sort of scales or what sort of frequencies, and the similar plot is on the right, but I won't focus on it now. So let me make you guess, if you throw a microphone, because that's essentially what it is, into the water and you're seeing this type of record, what do you think this is? Is it an earthquake? And the answer is no, but then what is it? So, it could be a whale. Well, let's take a look here. If you then look at the frequency, so that's the scale, the wiggliness, if you will. High frequency is lots and lots of wiggles, and low frequencies are slow wiggles. Whatever the signal is in the frequency domain, it's lines that are at very, very particular frequencies that it's capable of sustaining very well, and it gets louder and it gets less loud. So what this is a ship, okay? This is a ship that comes by, gets loud, and goes away. And these particular lines in the spectrum are because a ship is a turbine, is a screw that is rotating, and that sets up a very, very stable type of frequency of sound that you get into the ocean noise. So how about this one? This here looks like on a certain fixed time, there are these bursts of energy that happen in the time domain, and you see that also in the frequency. What goes into the ocean and on a timer makes noise? So this is also is from a ship, but so these are the implosions or explosions, if you will, of active air gunning campaigns by which we send energy down into the Earth's crust to figure out where the oil is. That's what ExxonMobil and various other Schlumberger companies are doing to shoot seismic lines nearby us. Third type of signal here doesn't look like either of those. Well, this is actually one of those waves that gets trapped into the sound fixing and ranging channel, which is a low velocity channel inside of the Earth's ocean, which traps energy very efficiently. And if somehow seismic waves get that energy in there, then it comes out at the location of the hydrophone as this broad swell of energy that contains lots and lots of frequency. But so this first one tells us something about ships, and that's not earthquake seismology. This tells us something about exploration campaign, which is also not useful for us. And this tells us something ultimately about the water, and that is not, to us that's noise. To other communities that might be signal. Finally, here are the whales, okay? So these are three examples of three different types of whales, and they have their vocalizations. They sing in a particular pattern, at a particular pitch or frequency, with a particular type of interval that is recognizable by their species, that also tells us something about the size of their organisms. And so you're seeing that none of these look like ships. None of these look like earthquakes, and in fact, we try to keep track of what it is so that we can have information for the biologists out there, but we are eliminating them from our records because they're not earthquakes and they're not telling us anything about the inside of the Earth. Here, then, finally, are two of these examples of actual earthquakes in the time domain, in the frequency domain, and here is the one that I showed you earlier already. That's the one at about 5,000 kilometers, about magnitude 6, and so it's a little blip of energy, a little blip here. This red is a little more than usual in an otherwise noisy channel, and so our instrument is capable of recognizing these patterns, these timings, these signatures of those earthquakes, and then saying, aha, that was a useful one. Now I'll leave my cruising depth, and I'll come back and report that to the satellite. And here are more examples. So my advisor, and I want to give him this credit now, Chris Collette, he was my postdoctoral advisor. Shortly after I joined Princeton, he then left for a new position at the University of Nice in France, and he came into a large pot of money to further develop this project. And that helped. And at the same time, I was sort of left on these here shores, and I did get collaborators, and to scale these, I tried to get funding also. So by area, that's how much money I got. And you know, you make do with what you may do. We should all remember that this is taxpayer-funded research, and this is cents on the dollar for what other uses of your taxpayer money are. And continuing to collaborate with the Europeans, then we were able to project through these various funding cycles. And so from that first prototype, and thanks to that sustained funding from the European Research Council, we were able to build the second generation MERMAID here. This looked a little bit like this. Essentially, the size and the color changed, but the various capabilities of the instrument were largely unchanged. It also had that main instrument, the hydrophone, pressure in the ocean that tells us something about earthquakes. And it had an antenna to report the data to get the timing right for right again every time it needs to be corrected. That it's capable of getting a new GPS fix, keeping track of its location, which only happens at the surface. I don't need to tell you that when you're at 1,500 meters depth, no GPS signal, no radio signal penetrates there, so you have to come up. And that's the only time that you get your location again and your timing correction again to make sure that you haven't drifted off your your proper timing. Here it is surfacing in the Bay of Villefranche in France. And so in generation 2, we accumulated hundreds of earthquakes, hundreds of records. And now I want to show you the two kinds here. Remember, I showed you early on that the little local ones, they're not telling us much about the Earth's structure, but they're telling us something about the Earth's activity, the Earth's crust, the Earth's faulting. That's a whole collection of small nearby earthquakes. This particular experiment was done in the Indian Ocean, and so we have a whole bunch, we have hundreds and hundreds of small earthquakes that happened inside the oceans at shallow depth, which were recorded nowhere else. And so that then helps us study the Earth's earthquake cycle, the Earth's frictional behavior, the difference between magmatic events and tectonic events, and so that tells us something about earthquakes. And then those two left columns here, those are the ones that actually tell us something about the structure of the inside of the Earth, because, once again, they are larger earthquakes, and they're farther away, that in order to arrive at this floating station, you have to go through the volume of the Earth, about which they're telling us something that we want to know, namely what the composition, the temperature, and the overall structure is. So here are examples. These P waves are those simply diving waves that go down and come back up and tell us something about the mantle. The PKP wave goes through the Earth's core, and so on. So we have, and PP waves are the ones that have bounced once and then bounced again and came back. And so over the various tens and hundreds of earthquakes and earthquake receiver paths, we are accumulating all of that various information with which to ultimately study, again, the inside of the Earth. So now I come to the final generation of it and the most recent excitement of it. I won't, so it's a third generation now, okay? So what we now want to do is we want to make this type of instrument that continues to deliver us ever better, higher quality data. We want to give it a longer life, and we want to give it, we want to have it go down to greater depth. And also, we want to make sure that it does something for other people, other scientists, other communities out there that aren't necessarily seismologists or don't care at all about seismology, but that care about the fact that we have designed a robot that can travel through the Earth's oceans and report data of interest. So the third generation looks like this here, and barring the color change, it's now become once again a sphere. It's now a glass sphere encased in that little jacket there. And it now can go down to several thousand meters and carry out this sampling job. And in addition to the hydrophone, which we've had in all these generations, on the side here, you can't really see it, there's an open port for another instrument. So one of you out there in oceanography or biological or chemical studies might want to plug in something that measures something else and that is happy to ride along our battery-powered instrument. There is a fourth generation. I'm going to skip that to show you more fun pictures here, but the fourth generation is going to have even more ports. And so this is, again, an example of trying to come together not just with the seismological community, but with a larger community of environmental sampling, or biological or chemical oceanography. Yes?
How do you lose them? Is it the battery dies?
Yeah. So when the battery dies, the instrument is defunct, and the end of life of this instrument is sort of governed by a UNESCO charter of what you need to do with scientific ocean trash. And so some of them, probably a very small amount of them, might be recovered if they're lucky. But ultimately, we do not recover those, and yes, this contributes to ocean trash, okay? But they're going to sink down to the bottom and remain there, and they will have had 5 years of good service in the service of environmental or seismology science, and so we will take that. So here's the inside. It's packed with batteries, okay? Because it's spherical, it's going to contain a lot. And the fourth generation, but I'm going to skip that, it's just going to have more ports, more capability, and contribute to more types of data. And I'm skipping this because I'd like to show you some of our campaign here, because just literally last week, I was in Japan with my students, one of them, the Portland native, Joel, Simon, and here is our latest instrument. Maybe it's going a little fast here. But so, early testing before deployment. This is the engineer who actually made this particular device. That's his design. His name is Jan Hello, working in Nice. And so we can carry it with 2 people because it has to be light. This is one of the main selling points of our instrument, that non-specialized ships can deploy it. If you should want to know what a ship costs to send out to an ocean, it will cost you $70,000, $80,000 a day just to get to a location. So our instrument is designed to be light enough that you can give it to passing ships who merely have to slow down to deploy it, and then they can carry on with their commercial or other business, not necessarily research business. Here what we were doing is we were testing that everything checks out before we're actually doing a deployment. There's Alex Berkeley, there's Joel Simon. And in this relaxed setting, we are testing the Bluetooth connection to the instrument, which goes through a series of steps before we actually let it go freely into the ocean. Here their roles are switched. They're learning. Okay, this was the Japanese ship on which we went. This is the Fukai Maru. Before going on, we actually wanted to make sure that it did float. It's a basic check, okay? It has to come up with this bladder inflated such that it's always at the surface. The rescue, the emergency, the default phase of this instrument must be, it's up there and it's trying to send where am I messages to the Iridium satellite. We slightly adjusted the buoyancy to make sure it didn't go too high nor too low. And then we designed the mission. So we programmed the instrument with a mission plan, and every time there is data to report, it also is downloading a new mission file from the server. So if something comes up in that during the mission, we can send instructions to the instrument to perhaps go down a little deeper, or be a little bit more sensitive about reporting, or maybe not care so much about the large earthquakes, or maybe target a little bit more of the non-local phases, and so on. And so we're on the Blackboard.